So, good morning everyone. My name is Álvaro Mena. I come from the University of Burgos in Spain, and I'm here to present this work that has been developed together with some other colleagues back in Burgos and my professor, Professor Vicente, who is chair of the Committee 215, and I'm really happy to be here. So this work is focused on flexural fatigue in fiber-reinforced concrete, and specifically about the analysis of the damage mechanisms that we can find in it. So let's start with a brief introduction. We know that fatigue of fiber-reinforced concrete is a really concerning matter nowadays. One of the samples is, well, the goal of this session. On the one hand, concrete is we are able to get concrete with more and more strength, and that leads for structures to be more sensitive, more slender, and therefore more sensitive to fatigue loads. And on the other hand, fiber-reinforced concrete, we are optimizing the dosages of fiber-reinforced concrete and getting more easily better behaviors such as strain hardening and so on. So that's why that's important. But however, there is a major issue when do research in fatigue of fiber-reinforced concrete of FRC, and this is the high scatter of results that we find, particularly when we subject specimens to high cycle fatigue between the same load levels. We can find, this is just an example, that if we have two equal specimens with the same dosages and subjected to the same load levels, we can find dispersion of about 2 orders of magnitude, for example, between 1,000 cycles and 100,000 cycles. Same dosage, same load levels. So how can we face this problem? Because the practical consequence of that, as you may know, is that the structural codes are very conservative. What the structural codes tell us with that is we have a lack of knowledge of what's happening with fatigue. So in this case, our research has been focused on flexural fatigue and a particular result that we obtained from flexural fatigue, which is the fatigue creep curves, which relate the number of cycles versus the maximum CMOD. We are talking about flexural fatigue in notch specimen. So this is the curve that correlates maximum CMOD in each cycle against the number of cycles. And with goals, we want to analyze these curves. 2 main goals: explore the damage mechanisms that appear in fiber-reinforced concrete and how they evolve. And the other goal is to look for damage parameters in these curves that can let us predict the fatigue life of the specimens and thus reduce the scatter of the fatigue life when predicting fatigue life. So we have manufactured 3 series of FRC, all with the same dosage except for the amount of fibers. This is the same dosage for all the series, A1, A2, and A3. The only component that changes is the amount of fibers from 0.3% in volume to 1%. And we have cast prismatic specimens of 75 by 75 by 300 millimeters with a notch of 1/6 of the depth, and we have cured that during 1 year in a climatic chamber. Here you have one specimen already broken. Sorry for that. And then we have characterized, before the fatigue test, we have characterized these 3 types of concrete, A1, A2, and A3. Well, here, maybe the most relevant is the compressive strength of more than 100 megapascals after 1 year, and obviously the 3-point bending test to characterize the static flexural behavior. This is the stress corresponding to the limit of proportionality, which is more or less the first crack strength, and here the ultimate strength, which is the maximum equivalent stress that the specimens reach along all the tests. Okay, so what you can see here is the ultimate stress is higher than FL in all cases. So what this means is that in all series we find a strain hardening behavior. This is once the specimen is cracked, the fibers are able to withstand more load than the matrix itself. So that's important to keep in mind for later. And finally, we have made the main tests, which are the flexural fatigue tests. Here you have an example of this. These tests are made on notch specimens, also uncrack. So here you see an example. We are a bit of a strange in Burgos. We do the flexural fatigue test upside down here with the two supports over here. The notch is around here, and here is the main support, right? And one thing that I have to say is that we have made, what are the load levels in the different series? Well, the load levels are between 16 and 80% of the average ultimate stress in each series. So that means that the load levels are different in each one, depending on the ultimate stress of each series, right? And now we're moving on to the results. Just a reminder, this is the sketch of a typical cyclic or fatigue creep curve in flexural fatigue with 3 different stages, being the second one the most relevant, the longest, and usually the one that indicates us how is the damage, the fatigue damage, evolving through the specimen, through the notch, through the crack. And this is also just a real example of what we have. So here we have the fatigue creep curves of the first series with the lowest amount of fibers, only 0.3% of fibers. And what we have found is that there is a double behavior here, because here we can see the usual S curves, fatigue creep curves, but here there's also a different region with a total different behavior. What is happening here? So what we have found, there is a primarily behavior in uncracked condition. That's what we can find here. If we make a zoom in over this region, we see that in this region, in this small region with very low CMODs, we also have an S curve. There is also another different mechanism of fatigue that is happening in the uncracked condition. So that's the main point of that. And obviously, this mechanism is exhausted around 0.05 millimeters, sorry for the units, which is more or less the crack region in which fiber reinforced concrete usually, the matrix usually cracks, right? If we move on to the A2 series with more fibers, 0.6% of fibers, we see that there is no a preliminary region of uncracked fatigue. We are not able to see that. Actually, there is a very, very short part of this previous region, less than 50 cycles, so that's why we can see here. And if we later see the fatigue creep curves of A3 series with 1% of fibers, we can see there is no previous section of fatigue. So what we saw is that there is a general case of the fatigue creep curves in fiber reinforced concrete, and this is shown in A1 series. Here are the same fatigue creep curves, but showing the number of cycles in relative terms. So it's better to understand and to observe the two mechanisms, this one in dot line and the other one in solid lines with different lengths and so on. So with this, with the example of this series, we can propose how is the general shape, the general behavior of fiber reinforced concrete under bending fatigue. And this is the shape, this is the double-edged fatigue creep curve that we are proposing, that we have actually observed. First, we have a region of matrix fatigue. In this region, remember on cracked concrete, what happens is that there are scattered microcracks along the notch, and fatigue loads are mainly resisted by the matrix itself. So the fibers, due to the low deformations, are not involved. And what happens once we reach this point, which is more or less, which is the crack point? What happens is that the fiber matrix bone fatigue starts. So what happens is all the microcracks converge in a main crack, and fibers start to actually work, and the adhesion between fibers and the matrix. So obviously this mechanism is much more ductile, and that's why we have more variation in CMOD. We are going to more CMOD until the final failure of the specimen is reached. So what are the conditions for having this double S curve? Well, two main conditions. First is that the maximum fatigue stress, which is that, has to be lower than the first crack strength. That's one of the points. And the other condition is that it has to happen a strain hardening flexural behavior, or actually, more precisely, the residual strength after cracking has to be higher than the maximum fatigue stress. So that are the two conditions for having this double S-shaped curve, the general case of the fatigue creep curves. Regarding this, there are two particular cases. One is if we don't have this and the maximum fatigue stress is higher than the first crack strength. So what happened when we have here? Well, during the first cycle, the matrix cracks, and we only see this second section of matrix. And what can happen in the other case? Imagine that the maximum fatigue stress is lower than the first crack strength, but higher than the residual strength. So what happens here? We only have matrix fatigue. Once the matrix cracks, the fibers can't withstand any more cycles. So we only see this second curve. With this reflection, with this proposal, we see that the number of cycles of a certain FRC specimen subjected to flexural fatigue can be divided in two parts: N1 regarding to matrix fatigue and N2 regarding to fiber matrix bone fatigue. Here we have, for all the specimens, the differentiation between the two fatigue lives. And what we see is only in A1 we have a certain amount of matrix fatigue, but matrix fatigue is just like disappearing as we move on to A3. Why? Well, because as we move on to the A3, the maximum fatigue stress is clearly higher than the first crack strength. So what's happening here, for example, in A3 series, during the first cycle, the matrix cracks, and we only see the second part. Is what is happening in this case, in A3 and A2, is this case. So we only see fiber matrix bone fatigue. Okay, so apart from that, the second objective was to try to find for parameters in the fatigue creep curves to predict fatigue life, try to understand what happened with fatigue life. And there is a very, very important parameter, which is the CMOD rate. The CMOD rate is the slope of the second part of the S curves. In the case that we have the general case, we have two CMOD rates, the one corresponding to the matrix fatigue and the other one corresponding to the fiber matrix bone fatigue. So we can extract this parameter and correlating with the number of cycles, each CMOD rate with the corresponding fatigue life. And here we have the plot in logarithm scale. What we can see here, we only have A2 and A1 in this part, vale? So in the one corresponding to the matrix fatigue, because in A3 there is no matrix fatigue. And here we have the three series, because in all the three series we have the red line, the one corresponding to fiber matrix bone fatigue. There is a very strong correlation between the CMOD rate of each mechanism and the number of cycles corresponding to that mechanism, around 0.9 of R square coefficient. So what is the implication of that? The implication of that is that if we know the CMOD rate of the matrix fatigue, here we have the implications. If we know the CMOD rate of the first part, we can predict the fatigue life until cracking, just until cracking. And if we know the CMOD rate of the second part, we can predict the fatigue life from the matrix cracking to the final failure of the specimens. So apparently, these two mechanisms are independent, but each one has the CMOD rate that are able to predict or correlates really nice with the number of cycles. And finally, there is another parameter that can have a certain relationship with fatigue life, which is the CMOD increase between sections, between the two mechanisms. In A1, in which we have this full curve, this general curve, we have found that there is a good correlation between the CMOD jump between the two mechanisms and the fatigue life. So that as this jump, this increases, the fatigue life becomes lower, with also a good correlation, but not as good as the one with the CMOD rate. So what indicates that? What is the physical explanation for that? Once the concrete matrix is cracked, there is a certain point at which the fatigue of the fibers of the fibers matrix bond fatigue is stabilized. So this value have certain change because it depends on the fiber distribution. So in some specimens, the jump is lower, in other is higher. So as this CMOD is higher, that means that the real section that is supporting the specimen is lower, and therefore the fatigue life becomes also lower. So that could be the explanation. And finally, a summary of the main results. The flexural fatigue behavior of FRC in the most general case consists of two mechanisms, matrix fatigue and fiber matrix bond fatigue. And according to this, we have shown the general shape of this curve, establishing the conditions to observe this double curve and also the particular cases that we can see. On the other hand, it has been found a really nice correlation between the CMOD rate and the fatigue life. This relationship seems to be independent between the two fatigue mechanisms that really act. And finally, there are some others parameters of the fatigue creep curves that can enable us to predict fatigue life.